Good day everyone. The topic that I'm going to discuss for this video is about Cauchy sequence. Now, when can we say that the sequence is Cauchy? Here, consider this definition. A sequence of real numbers is a Cauchy sequence if and only if for all or for every epsilon greater than 0, there exists a positive integer n sub 0 such that n and m are greater than some positive integer n sub 0, which implies that the absolute value of the difference of two terms in the sequence a sub n and a sub m is less than epsilon. Note here that the concept is almost the same as the limit of the function. But here, we have two positive integers, n and m, greater than any or greater than some positive integer, n sub 0, wherein we have this condition. Now let me discuss this. So we have this one. We know that by using the concept of absolute value, we have this. And if we add a sub m to both sides, we have this one. So notice if we have this inequality, we say that this term here, a sub n, belongs to the open interval a sub m minus epsilon, a sub m plus epsilon. Okay, so let us try to consider the real number line. We have here a sub m. So say this is our a sub m minus epsilon, and this is our a sub m plus epsilon. So for any epsilon, this open interval depends on our epsilon. If we make our epsilon, this one, the distance from this point to this, if we make it smaller, so our open interval becomes smaller. Okay. Now, in this case, it means that for every for open interval a sub m minus epsilon to a sub m plus epsilon, there is a term a sub n within this open interval. So say for example we have here, here is our a sub n. So it could be here as long as within the open interval. Now take note that it depends on our epsilon. If we make this epsilon smaller and open set, still a sub n is in the open interval. So most of the, by the way, this is for all n m greater than n sub 0. That case. So most of the time, this happens when n and m approach to infinity, or n and m get large. So as you observe here, again, depending on the epsilon, whether we can make it as small as possible or not, inside the open interval, there is a term in the sequence, say a sub n, for all n m greater than n sub 0, or as n and m approach to infinity. In other words, we say a sequence is a Cauchy sequence if every two terms are closer to each other, or in general, a sequence is a Cauchy sequence if and only if the terms of the sequence become arbitrarily close to each other as n gets large. So, kumbaga, murara na siya og uyab, Cauchy kaayo. Okay, let's have here a theorem that states that every convergent sequence is a Cauchy sequence. So here, we suppose that to prove this one, we suppose that the sequence a sub n is convergent. This is our assumption, that every sequence is, that every convergent sequence is Cauchy. So it means if a sequence is convergent, then the sequence is Cauchy. So for a convergent sequence, that is our assumption. So let us suppose it here, assume it here. Then we will show that the given sequence is Cauchy by using the definition of Cauchy sequence, using this one. So we will show this one, that for every epsilon, we will try to find the existence of positive integer and sub-zero such that we have here, and we will show this one. So since in our assumption that the sequence is convergent, then for every epsilon greater than 0, there exists n positive integer n sub-zero sufficiently large. So sufficiently large. This is from the definition of a convergent sequence. Such that we have here n is greater than n sub-zero implies this one, a sub n minus b. Here, as you notice here, we use here 1/2 epsilon. 1/2 epsilon. So, we have a goal for this one. Why we're using here 1/2 epsilon? Because later on, we will sum it to get epsilon. So, still here, this is the definition of a convergent sequence. Accordingly, here, as you noticed here, n, m are greater than some positive integer in sub-zero. So this implies, because this is our goal from our definition of Cauchy sequence, and of course, if we are going to add this one, this by the way, let's have if we're going to add this one, this becomes 0, right? So we just subtracted b and then added b here, make this one, they're just equal. Then less than, we separated the absolute value, and from this one we know that this one is less than 1/2 epsilon and this one is less than 1/2 epsilon. Now as you noticed am minus b, we have b minus am. They're just the same because as if we are going to factor out -1 here, of course the absolute value of -1 is 1, so they're just the same. So if we add this one, the result is epsilon. Therefore the sequence is Cauchy. So that's it. Now let's try some examples here. Now let's consider constant sequence. This one. Actually, I already discussed this one in my previous video. So we have shown that this constant sequence has a limit too. And of course, since this sequence has a limit, therefore we can say that this sequence is convergent. So the sequence converges to a constant number 2. So by using the previous theorem that every convergent sequence is a Cauchy sequence, therefore this sequence is Cauchy. So the same thing, the same for this example. So I have discussed this one in my previous video, that this sequence is convergent because this sequence has a limit 0. So it converges to 0. Therefore, by using the previous theorem, this sequence is Cauchy, or this is a Cauchy sequence. So that's it. Now, in my next video, I'm going to discuss the concept of completeness. When can we say that a sequence is complete? So in that case, we will be using the concept of limit. So that's it.